Okay, so welcome to today's lecture, and as always, any questions about anything that was before that we can discuss before we start? And I guess if not, then we just start. So it's not everything that we're going to talk about today, so we're going to, I couldn't really estimate the speed with which we're going to go, so we're going to break somewhere in the middle of this whole thing and continue it all tomorrow. So we started talking about the pointers yesterday, not yesterday, last week. And last week we talked about the non-owning pointers, so the ones that don't own the memory, they just point to something that is owned by somebody else. Today we are going to talk about the pointers that own the memory and the way they're used to. But before that we are going to, so then we're going to dive into the representation of the memory. So before we were talking about the scope and so on. Now we will understand why the scope works the way it works, and maybe it will give you more intuition about how it works. And in the end, I don't know if we reach it this lecture or tomorrow, but we are going to talk about the smart pointers, and this is the modern way of dealing with memory and allocating memory in C++11. So let's start with that. So we were talking about the pointers in the last lecture, mostly that point to arbitrary types that we've already seen, like simple types, like fundamental types, like integer, float, and so on. But they can also point to objects, and when they point to objects, there is a new syntax that we didn't see before. Well, I guess you have seen it before, somewhere like in Java and so on, but we didn't discuss it in this lecture yet. And the syntax is this line over here. So if you can easily point to an object of your own class. For example, like if I have my class and I declare an object of it, I define an object of it, then I can create a pointer to it, and I can access all the methods with this line kind of arrow over here. And this arrow is just a syntactic sugar for us in C++. It's actually, to the compiler, it looks like this. So it dereferences the object, and then it calls the function of a dereferenced object. So if you remember the pointer that points to something, you can dereference it. Dereferencing means taking a value under the pointer. So it takes the value under the pointer, and then it calls a method of it, right? I hope that makes sense. But generally, we use this syntax when we want to call a function from a pointer. Good. So we were talking a bit, and you actually had to do some homework on it, about the polymorphic references. And I hope you understood that it's a bit of a pain with all this const referencing and so on to put it in your class. The good news is that you don't really have to do it. It was basically to make you understand what a reference is and how to deal with it. But in general, people use pointers for that. And they work in just the same. So you can create a pointer to a base type from an object of derived type. So for instance, if I have a derived object and they are in the relationship that derived is a child of a base class as usually. So this derived object, you can set its address to a pointer of a base class. And we're going to see a lot more examples on it. This is the standard way that you implement polymorphism in C++, and we are going to work with it a lot. Right, so the only difference between, like if you understand references, then you basically understand pointers. You just need to add one more thing or actually two more things. It's first, the pointers can be reassigned. So the reference, you can only bind it to one variable, and it can never change its binding, right? So it will only be bound to a single variable. It cannot change it to another. With pointers, it's not the case. You can set the pointer to one thing, then set the pointer to another thing, and it's totally fine. Second thing is that the reference cannot point to nothing. It must point to a valid object in memory. It's not the case with pointers. So the pointers can actually point to nothing, and that is what the null pointer is for. So whenever your pointer points to a null pointer, it means it points to nothing. And that allows us to store so it means that you can create pointers like uninitialized basically, which allows us to store them in a vector. Because if you need, like if you want to put something in a vector, it has to have a default constructor, which means it has to be initialized without parameters. That is not the case for a reference, but it is the case for pointers, so we can store them in, say, a vector or an array or something like that. And this is very handy, which we will see on the next slide. There is just a small example for you. It's, maybe we'll go deep into it, maybe not. Also, you probably have a say on it, like if you really want to, we can. But the idea is that you did implement the strategy in the homework, or you are implementing the strategy pattern in the homework, but you're implementing it with the const references. And the issue with that is, if you remember, you needed to pass like some dummy reference in order to initialize your object, because you had to initialize a const reference in your class. This is not the case for pointers. You can just set them to null, and then you don't need to pass anything into your constructor, and you can set and reset that pointer at any point of time. So I hope that makes sense. We are gonna probably stop on it a bit later too. So just a small example about pointers and how to use them so how to use their polymorphism is a small example like this. So again, I use structs here because classes take one more line to say that we want public. So I will use structs here, but generally it should be implemented as classes. Otherwise it doesn't fit on the slide. So the idea here, again, it's a very simplistic example, but it shows off the concept. And as usual, try it out and so on. But the idea is you have some abstract shape. It doesn't matter. I mean, print is not a best function for abstract shape, but it can be any, like say it could be area function or something like that. And any shape can probably compute its own area, and that would be a nice function to have. But for now it's print, just to make sure that we can actually see what happens there on a single slide. And let's say that we have, so this is our interface, abstract shape. So it's not like, it just has the pure virtual functions, so they must be overridden by somebody else. And that is exactly what happens in square and triangle. They're both children of the abstract shape. So you can say that a square is an abstract shape and a triangle is an abstract shape. And they override these print functions to print square and triangle respectively. The cool part comes when that we can store them in a vector without knowing what we store in the vector. So you can have a vector of pointers to an abstract shape. You don't care if it's a triangle or a square, but this is just a vector of abstract shapes. And then you create a square and a triangle, and you can put both of them into this vector. At this point, you don't have to know what stores in the vector as soon as you've created an object correctly. The overriding of the functions and the virtual tables of the classes, they will help you and they will tell you what object is actually stored there. So now if you run this line, it will actually print the square and the triangle just as you would expect. And again, try it out, copy, see that it actually works. If it doesn't, tell me, but it is, like it does. So the cool part now is that you just get an abstract shape over here, and then you just call print on it. I use here auto because, again, it saves space, and I would say it's not a bad idea to use auto in modern C++. You can use it with const, you can use it with star, and the compiler will find out which type should there be. So in this case, it will find out that this is actually an abstract shape instead of auto. Okay, does that look clear? Like, does it make sense why that's useful and that we can store all those abstract things in a vector? So like why we want to do it is now if we have a function that takes a lot of shapes, then we can just pass to it some abstract shapes, and we don't care who creates them and how they create them as soon as they conform to the same interface, right? So it is a very powerful tool for designing programs that are decoupled, like where modules are decoupled from each other. So just like with the strategy that we had before, like you don't care what the strategy is. Your class image, for example, wouldn't care what the writing strategy or reading strategy is. It just cares that this strategy conforms to some interface, right? So that's exactly why we do that. Yeah?
Why do you use the star operator in
here?
Yeah.
That is because the pointers are declared like that. So the pointers, whenever you declare a pointer, you say type star something. I think we're gonna see that soon again at how to declare pointers, because we can also use const with pointers, and at that I think I will dive deep to make sure that you all understand how we declare pointer, how we use const with pointers, and so on. So I will probably answer your question in a couple of slides. Yeah?
In line 17, why do you use the and sign and not the star?
This one? Because this is just a variable in my local variable, right? And my local variable to initialize a pointer is just a store. In a very simple way, it's a storage of an address of a variable. Okay? The pointer also knows the type of that variable generally, but for now it's not important. Let's just consider that a pointer is just a storage of a address in memory of some variable, right? And this operator, like if you put this kind of and sign or ampersand before a variable, it returns its address. That's so it kind of can get a bit confusing with references and just using this ampersand without it. So whenever you have a type before an ampersand, it will declare a reference. If you don't have the type and you just have a variable name after the ampersand, it gives you the address. Okay? So in this case, this gives me an address of wherever my square is stored in memory. It can be anywhere, I don't care. This operator gives me the address. And if it gives me the address, then it basically creates a pointer. So you can create a pointer to a square or to an abstract shape from a, okay, I think, again, let's try to do an example. Didn't create a file yet. Okay, so if I have a main, and let's say I have some struct, I don't care what, let's call it A. Good. So I can create a pointer. So first of all, I can create a local variable of A, and let's have maybe some, whatever, integer A equals 10 or something like that, right? So I can create my variable A. Let's also again okay, so I can see out like a dot A, and if I run it, it will print out 10 as expected, right? So that is like we've done it like literally hundreds of times by this time. So what we can do is we can also create a pointer. So a pointer, whenever you put a star after a type, you declare a pointer, or you define a pointer. It depends on if you give it a value. So let's say we create. So we can have a uninitialized pointer, a pointer, and this pointer can only point to variables of type A, because that's what we say. We say it is a pointer to type A. We cannot set it to integer. We can't give it. We can't point it to an integer. It knows that it must point to type A. Okay. So generally, as I told in the last lecture, it's a very, very, very bad idea to not initialize the pointers. And there are two ways to initialize them. If you have something to initialize them with, something like an address of a variable, you can say equals address of A. So what did I do here? So it's a lot of syntax, but bear with me with this. So generally, whenever you see either a star or an ampersand after a type, you declare, like, it becomes part of the type. So here there is a star over here, and it becomes part of this type. So the whole type of this variable is a star, and a star is a pointer to a. You always read them from the right. So the types, if you read them from the right, it makes more sense, even though it's counterintuitive to read something from the right. But if you read those types from the right, it makes more sense, because then you say it's a pointer to a. Okay? Right. Now the ampersand. So the ampersand doesn't have a type before it, and therefore it's just an operator that gives me the address. So what it tells me is that this is the address of A, and we set it to a pointer to A. Through this pointer, we can access A just as we did before, but using this syntax of arrow. Yeah, sorry, it's not A, it's a pointer. Right. So if I run it, it prints out 10 again, which is good. And just to show this, I can also dereference a pointer. Come on, where is it? Like this. Because again, now the star does not follow the type. And if it doesn't follow the type, it becomes the dereferencing operator. So now this thing is actually a variable under the address of this pointer. Does it make sense? Or not really? It's too many symbols? Okay, so who is fine with that? Or okay, so everybody is mostly confused. Right, so the simple rule is whenever you see either a star or an ampersand after a type, it defines a type. Okay? So if I have okay. Right. So let me remove these guys. Okay, so let's focus on the lines 9 to 11, right? The first line, the line 9 defines a variable a of type a. That should be clear by now. The aref variable, so this thing declares the variable aref of type a ampersand. A ampersand is a reference. So because ampersand appears after a type, it declares a reference. Okay? So now aref is a variable of type reference to a. Okay? Good. So, and now the same goes for the pointer, but with a star. So now this a pointer is a variable of type a star. So it's a variable of type pointer to a. Okay? So they both, like these guys, they both point to a real variable in memory. The difference between them is that you can point this guy to somebody else. So I can, if I have, so right, now how to initialize them? I can pass here just a, right? We've seen it before. And the reference will be initialized as a reference to this a. Now, these are virtually the same. Like if we modify aref, it will modify a. If we modify a, aref will also be modified because aref is just connected to that variable. Okay? If we want to initialize the pointer, we need another symbol. We need to say, we give it an address of a variable. And now this ampersand does not appear after the type, so it doesn't mean the same as this ampersand over here. It's a different ampersand because it doesn't have a type before it. And because it doesn't have a type before it, it's called an address operator. It always returns you the address of a variable, right? So in this way, we initialize a pointer to be an address of something. And if we just print, say, if I print a ref, I will get a value. So let's say that it's a reference. I forgot. Come on. And the pointer thing, if we just print the pointer, we will not see the value under it. I can't do that. Okay, let's maybe. Yeah. I just want to show the difference between them, and for that, for a second, we're going to switch back to int, because I cannot print a, because it doesn't know how to print a, but I can print int. So if I run this thing, you will see this output. So the reference is 0, which happens to be the value of this integer a that we've created, right? But the pointer is some complicated address in the memory. It's this hexadecimal number, so base 16 number, but it's just a number. It's just a number of the cell in the memory where this variable is stored at this point. Okay? And if I want to get a value of it, like now we can, I guess, switch back to a. So if I want to print a value, I use .a here and arrow over here. It's just the syntax that we use for pointers and references. So a reference, you can work with it just like with the original variable, but with the pointer, because you are actually working with an address of that thing, you need separate syntax. You need this arrow over here. Okay? I hope that cleared up things a bit, because that is important. Like, we need to understand that to go further. So let's try to, like, that everybody is happy with it, and then we'll go forward with it.
What does aref.a mean?
It's just this variable of, so aref is a reference to this variable, and this variable has some field a, right? It's just some data field. Should I name it like differently from a? Does it confuse people? I mean, it can be like whatever, data or something, right? Okay, because I understand there is a lot of a's going on there. So, right. So now they print exactly the same thing, and if I change now my variable, so my data in my variable, let's say now it's going to be 20 instead of 10, and let's say I will just move these guys. Let me just copy them. Okay. So I copied them downwards, and you see that I didn't touch these variables. So the aref and a pointer I didn't touch. I actually changed the value of the a variable, right? But because they both point to it, their values will change too. So now if I run this and extend the view a bit, you can see that initially the reference and the pointer are 10, but then when I change a, they change their value because they just point to that variable in memory. They don't have a copy of that variable to work with. They just point to that. Okay?
When do we use pointer? When do we use reference? What's the difference between their usage?
The only difference between them is what I was telling on the previous slide, is that when you need something to be nullable, so to not have a value, you use a pointer. So if you imagine, so an example, like a good example would be the strategy that you had to implement for the homework, right? If you remember, the initial task was to provide a dummy strategy to it, because otherwise you couldn't create a class, right? This way you don't have to do it, because you can just set it to null, right? To null pointer. Like, if you would use a pointer instead of a reference, you would be able to not initialize it. You would just say, well, it's a null pointer, and if I then try to call it, you would just check if it's a null pointer and not do anything if it's null pointer. So you wouldn't need that boilerplate, and that is generally where you use pointers. Like, most of the times, for anything related to design, like interfaces and so on, we use pointers. For passing parameters to functions, generally we use references, like for passing big parameters into functions that we don't want to copy. Then we use references. But generally the difference is that you can reassign a pointer to another thing. So for example, if I have here another class, like another object of type A other, what I can do is I can say this pointer equals address of A other. And if I run it, again, let's make the A other, this will not work, A other data equals whatever, 200. So now what you see here is that I have just changed the address that I store in my pointer, right? So I say, okay, I don't care about the variable A anymore. Now I care about the variable A other. So I now set this pointer to an address of another variable. And I cannot do that with references. I cannot reassign the reference to something else. I can do it with pointers. And that's why they're more versatile for your like design purposes. Like when you think about how your classes should collaborate, how should they, like, is this class the same as that one? So anytime you want to convert your derived class to a base class, you generally use pointers. We did use references before just to make sure that you understand references, because that's very important. But generally, we will be switching to pointers from references. And I hope it will be an easy switch now, because they behave in a very similar way, apart from a small syntax change and the fact that you can reassign pointers. All right, so I hope that got a bit clearer. I understand it can be a bit harder because we discussed pointers like last week, and yeah. So let's try to make sure that we're on the same page here.
But now it's somehow like a strategy.
Yeah, like that's like.
What's again the difference between a strategy?
So a strategy is a design concept. Like you use pointers and references to make sure that your strategy works, for example, or any other concepts that you use to make sure that you decouple the logic in your program. So when we talk about the strategy, we're talking on a very high level about our code. We don't think in pointers, we don't think in references. We just say, I want this functionality and I don't want to care how this functionality is implemented. That's what we're saying. And then when we actually want to implement it in code, then we think, okay, so what tools do I have in this language to implement it? And in C++, we have either references or pointers to implement it. And generally, pointers are better suited for that, but we use references just to make sure that all the concepts of references are clear at this point. Okay. Good. Then a lot of you have already used this pointer, and I guess this is something that you got used from, like if you use Java at any point of time, it's this pointer. So every object has a pointer to itself. Like every object of a class or a struct that you create has a pointer to itself, and this pointer is called this. It's just a pointer, and you use it just the way you use any other pointer. If you want to call a function from it, you can provide an arrow to it. If you remember when we were talking about the assignment operators, assignment operator has to return a reference to self, like to the actual object. And that is done by returning dereferencing of this. Again, it's not too important because mostly you can use all the data members and all the functions in your class without using this. It is relevant if you're doing some really hardcore template programming in C++, which we didn't talk about yet, and it's not relevant for the course, so we will not dive into that for the course a lot. So it's just for your information that there exists such a pointer, but most of the times you can omit it, apart from when you need to return a reference to your own class. If you want an example on that, then go to the lecture where we talked about copy constructors, assignment operators, and so on. And there you will see an example how it is used. And I guess this is really the only example where we will use this in this course. And you generally shouldn't need to implement your own assignment operators and so on. So it's mostly for just your knowledge that there exists such a pointer. You probably won't really need to use it in this course a lot. Good. So this slide is kind of important. It's, as you might have understood already, const is an important word in C++, and sometimes if you don't really understand it, then it can backfire. You can be confused at what it does, and the compiler can be unhappy, and so on. So we add some more const here, and this const is, I guess, a bit more complicated. But if you remember to read the types from the right, then you won't have many problems with that. So there are a couple of flavors of using const with pointers. A pointer can point to a const variable. It means that the variable under the pointer is constant, but the pointer itself is not. So you can change this pointer to point to some other variable, but the variable under the pointer you cannot change. So it looks like this. You say, like reading from the right, it's a pointer to a const type, right? It means that you can set it to some address, and then what you can do is you can reset it to some other address. But you cannot change the value under this pointer. So if I would try to call a non-const function of this variable, or I would try to dereference it and set to something else, that would not work. It would give me an error. And again, try it out. So copy that, try what you can do with it, what you cannot, see what errors it does on these two lines. Because when you're working on these two lines, your errors will be bearable. You will understand where they come from. And then maybe you will remember where these errors come from, and when they come up in a bigger program, you will know, okay, I know where it comes from, right? Then the second const is pointers can be const, but point to a non-const variable. So again, reading from the right, it's a const pointer to my type. So it means that the pointer itself is constant. You cannot reassign this pointer to another variable. So you cannot do this. But you can actually change a variable under the pointer. So if I would have some data member called A in my type, I could write something like this, even though my pointer is constant. And then there is a relatively easy way where everything is constant. You say it's a constant pointer to a constant type. You can't do anything with it. You can just pass it and use it in a constant way. So this is most similar to the constant reference.
Why should a pointer should be constant? Because you're saying pointer is something that we point to different things. Then
yeah.
Why should it be constant?
So for example, it's not really used because you can see that this syntax is not really intuitive, so people don't like using it. And generally, you won't ever need to use this, like this syntax, for example. Mostly people use this. So this is most commonly used.
The second one, it's nonsense.
Yes, I agree. That's why you never really see it in real programs. But you need to understand what it means, because otherwise, if you ever see it, you will say, whoa, what does it mean? Why did people do that? So at least you have to know that you have to go to those people and explain them that they're wrong. But you need to know what to explain, right? So it's important to understand that because it kind of maps to the concept of memory. And if you understand that, you won't have problems with, like, it kind of teaches you the logic of thinking in addresses and the variable under some addresses and so on. So a pointer is nothing else as another variable that just stores an address. And in this case, for example, the pointer variable is constant, so you can't reset it to another address, but whatever it points to is not constant, so you can change that. And it doesn't really make sense usually. Mostly you want this. Like for instance, if I would pass a pointer into a function, I would probably pass it like this, because I care about my variable not being changed, but I don't care if somebody resets this pointer to something else, because he will be working with a copy of my pointer. I hope that kind of is clear, because a pointer is just a variable. And again, if you read it from the right, it kind of tells you what it means. So if you remember this slide, you won't have any problems whenever you see const with pointers. But then again, we will come to other pointers that we mostly will use, and mostly we're going to use this for raw pointers, and these things are nearly never used. Right. So at this point, we've finished the non-owning pointers. There is nothing else to tell about them. If there is something that is not clear yet, it's a good time to clarify that and clear it up, because we are going to go into the memory and how the memory is, what types of memory C++ has, and it's a good idea to understand, at least like have a feeling that you have an intuition about pointers at this point. So if anybody, like, everybody is happy for now with how you feel about pointers? Okay, I see mild nods. That is good enough for me, I guess. Good. So we're gonna talk about memory. I explicitly pushed this lecture very far behind in the course. Usually when you start talking about C++, this is one of the first lectures that you get. And I believe it scares you if you don't understand anything about C++. At this point, you've done a couple of things that are more hands-on, that are more realistic. So now you shouldn't be really scared too much about the syntax. And now we can talk about what happens under the hood. So we were talking last lecture about the working memory, that we have some memory allocated for our program. And it's not enough to just say that we have some memory. We also have structures to control this memory. And this memory is generally divided into two parts. The first part is a stack, and the second part is a heap. So a stack, you can think about it just as this stack of coins. So in order to get to this coin, I have to lift up all those coins, and then I get to this coin. And that's the idea of the stack. While on the heap, I can kind of like look through it, rinse through it, and it will take me a bit more time because it's generally bigger. But then eventually I will find something, and I will find it in logarithmic time, which is relatively quick. So, and that is how the memory is separated. So we have a stack and we have a heap. And we are going to talk about now what they are used for, why is it done that way. Good. Stack. So stack is a static memory. It means that whenever you define some variable or an array that has a static size, you are allocating this memory on a stack. So most of the times, I think all of the times that we were working with variables in this course for now, we were allocating things on a stack. At least like all the simple variables. It is generally a short-term memory, right? So you allocate something and it lives until the end of the scope. So in the end of the scope, everything dies, and we are going to look into example why that happens, but the idea is that every single scope is a small part of the stack. Every time you open a scope, you create a new stack, then you put things in the stack when you allocate variables. In the end of the scope, the stack empties completely. So you just throw away all your coins in this stack, right? And it's generally relatively small. On most systems that I know, it's 8 megabytes, so you cannot allocate more than 8 megabytes of data on your stack. But the memory allocation is really fast. So whenever you put something on a stack and remove something from a stack, it's fast. And that is a good idea to keep your stack small, so to keep scopes small, to keep functions small, and so on. Because the smaller the stack is, the less time it takes for the compiler to look through it to find the variable that you're referring to. So if I have a huge stack, if I have a huge scope, for example, with thousands of variables, and then I try to reference a variable that I used really, really high up top, the compiler, or like the runtime thing, will have to go through the whole stack, find that variable, change its name, and then put the things back on top of it, which takes time. So that's why it's a good idea to keep your scopes and functions small. Right. So the stack has only two operations. It has operation push and operation pop. Push, pop puts a new coin on the top of the stack. Pop takes this coin away, right? There are no other operations. You cannot access things from the bottom. You cannot access things in the middle. There is no indexing. There is nothing like that. You can just put things on top, take things from the top, okay? And let's look at the small example here. So there are some printing statements that are not the things that we used, but I didn't really want to adapt that from the previous years. So this printf, just to make sure that you're not confused, it just does the same thing as we do with cout and cr. It's just a different function to print things out. Right. So everything else should be quite familiar to you. And let's say we have an improvised stack frame over here. It's not, of course, the real stack, but I feel it's good enough to give you intuition about it. So we're going to go through this program on what happens line for line and say, and try to figure out what happens to the stack. So what we do is we start with the first line and we define a variable size, and it's equal to 2. What it does, there is a command on the stack. It pushes an integer onto the stack, and it pushes it over here. So, so that's our first coin in our stack, right? Then we create a second variable, and this variable is a pointer. So it's a pointer to an integer, and we point it to a null pointer. So what it does is we push a pointer to an integer onto our stack. Again, a pointer itself always lives on the stack. It's a local variable. It's a local variable of type pointer to integer. And this is exactly what we see. So we've put into our stack a variable pointer, and this variable has a value of null pointer. Okay? Then we enter a new scope, and what we do is we create a constant size array. So it's an array of size, in our case, 2. And what happens is the compiler knows, okay, it's an array of size 2, and I need to put 2 things on my stack. We don't initialize those variables just yet, because we didn't. It's not really a good idea to do it, but I think it's a good way to illustrate what happens. So what goes on is it puts an array 0 and an array 1 variables onto the stack, and they have no value for now. So they just have some uninitialized value to them. If we go to the next line of our program, then we set the value to the first one. We set the value to the next one. We don't do any memory allocation. We don't remove any memory. And then let's say that we set our pointer over here, which is the same pointer as this guy. We set it to this guy. And the only thing that might be a bit unclear here is that the static arrays, like the constant arrays in C++, they can be treated as pointers. We did briefly touch that on the last lecture, but here you will have to believe me that you can just set this pointer to this guy, and it will set the address of the start of the array into the pointer. And this is what is shown here. So we say our pointer now points to address 2, and it's red here because of this red. So it just points to this frame of our stack. Was that clear? Okay, cool. So now our pointer points to that thing, and now we reach the end of the scope. So the scope has ended, and the scope does 2 times pop, because it remembered that it allocated in this stack twice the memory, so it needs to remove everything until the point where this thing has started. And this is done automatically for you. Like, this is the beauty of C++, that it manages its memory based on scopes. because this guarantees that you don't lose memory if you do everything right, and you don't need any garbage collection because everything will be accumulated on its own whenever it reaches the end of the scope. All right, but we now have a problem. So this is exactly what we should never, ever, ever do, because this guy still lives, and now it points to an address of something that is not there in memory anymore. So it still points to the 2, but the 2 is empty. So if we try to print things out, it's undefined behavior again. Our program might break. That is a good thing, because then we know that we did something wrong and we can start searching of what we did wrong. But it can also print out some variables which are still there, even sometimes the old variables which are still there. So, and then in the for loop, we will just print those things out. I will skip that now. It's just to show that it will not work, that there are some values there that don't have a value anymore. And in the end of the scope, we have 2 more things left here. In the end of this scope, we need to remove everything. And by default, C++ will remove everything, that it allocated in the main function by the end of this main function. And the same thing happens for every single function that you write. Okay, the same thing happens for the classes that you allocate, for your custom objects and so on. It all happens automatically because of the stack. So I hope that was clear. So now you understand that the scopes are just they're markers for the stack until when to remove things when the scope is closed. So when you open a bracket in your scope, there is a marker on a stack that, hey, here I opened my scope. And then you do something, and when you reach the end of the scope, the stack knows that it has to remove everything until this marker on the stack. And therefore, you guarantee that everything is cleaned up. Good. So I hope that also cleared up the issues that you have with memory that points a bit too far and so on. Right. So now let's talk about the heap memory. We didn't explicitly use heap memory, but we did implicitly use heap memory. Whenever you use a string or a vector, it's just a class that allocates memory on a heap. You don't know about it, but it does it for you. And we are going to talk about, so heap is a lot more complicated than a stack. A stack, I explained to you in basically one slide, and I hope that was relatively clear. There is really nothing else to explain about the stack. The heap is a bit more complex because it is dynamic memory. You can change things in this memory. You can change the size of arrays and so on, and you have a lot of this memory. You can have, if you have a stack of 8 megabytes, your dynamic memory your heap memory can be as big as your RAM, basically. So it can be 4 gigabytes, 8 gigabytes, 16, 32, whatever. It's available for a very long time. So until, you can create something in one function and it will still be available in another function if you can pass a pointer to where it's stored. So it's not automatically cleaned for you when you go out of some scope and so on, because the scopes are only cleaned because it cleans the stack. Whatever is not on the stack is not affected by getting out of scope in any way. And because it's not automatically managed, we have to manage our memory ourselves. And that is where most of the complexity of C++ memory model comes in, and why a lot of people had a lot of issues with that, and why now people have implemented smart pointers and so on to manage that memory for us in a nicer way. We are going to talk about all of this. Generally, historically, whenever we need to create memory on a heap or remove memory or free memory on a heap, we use the keywords new and delete. Generally, the allocation is slower than in a stack because your heap is much bigger and the data structure is a bit slower, but it's the only data structure that you can actually manage for such a huge amount of memory. Right. So for example, whenever you need to find a particular coin here, you will actually have to search for this coin. There are some rules how to, a heap is just a data structure that guarantees the access of logarithmic access to anything on the heap. But you can think about it as basically just looking through the heap and of coins and then finding it. It's probably faster than if you would have a huge stack of those coins. If you would go like from the top to the bottom, it would take you a long time. It's worth it for a small pack of coins, but it's not worth it for a lot of coins. And for a lot of coins, it's much faster if you just scatter them around and search for them. So that's the intuition why we use heap and stack. Okay? Right, so there's going to be a lot of these guys in this lecture. Most of the examples that we're going to see today are not going to be the ones that you will ever be using in real code. But I feel like it's important to understand the basics, the concepts of what we had to do before. And then in the end, when we get to the smart pointers, we will get to the power and beauty of C++11, where we don't have to do this all manually, but it's still important to understand why it happens that way. Right, so whenever a user controls memory allocation, it's bad, because users are unreliable. Like, I'm unreliable, I don't trust myself allocating memory or deallocating memory, because I will definitely forget that. And the issue is that, you can use new to create memory on a heap. What you say is you basically, well, you create a pointer, so this pointer lives on a stack, and you set it to a null pointer, which is some address somewhere, you don't care. But it's just some address that you cannot dereference, so it's nothing. And then what you do is, now you want to say, okay, now I want this pointer on a stack to hold an address from a heap. And the way you do it is you say, well, I use new over here. So you say new int, which allocates me a single integer on a heap and returns a pointer to it. So new returns a pointer to somewhere on a heap, somewhere in your memory on a heap. And yeah, you can also do the same thing for arrays, but it's not really relevant for the course, so it's just there for you to know that it exists if you see it anywhere at some point in the real world. But we're not going to focus on that in the course. I will try to keep on every slide that I don't encourage, I will try to keep an alternative, like what you actually have to use. So when you go back to this slide, so that you're not confused and you're not actually trying to use something that I don't really recommend using. So we don't know what smart pointers is, but it's for a future you who will look in these lectures and who will know what a smart pointer is. So at this point, you have to stop looking at this and go looking at the smart pointers. Right, then for new, there is an operator delete. And it is important to remember that the memory is not freed automatically. You cannot free your memory automatically. Nobody will fix it for you unless you do it. And that means that you must remember to free this memory. So if I create an integer on a heap and I pass it to here, then now my pointer has some memory address from a heap, and if I now go out of scope, for example here, then it will remove my pointer, but it will not remove the allocated memory on a heap. And the problem of that, we're going to talk about it a lot more, but the idea is that we'll lose some memory that will never be accessible to us anymore. That's why like badly written programs grow their memory usage over time. That's why you have to reboot Windows time from times, for example, and so on. That's all about memory that somebody allocated, nobody reclaimed, and at some point you run out of memory because of mistakes that the programmers made. Whenever we need to manage that manually, we will do mistakes. So to free memory on a heap, you use delete. So if you pass delete, if you pass a pointer address into the delete, like a pointer into the delete, what it does, it frees the memory under the pointer. So it says, okay, I don't want this memory anymore, so take it back from me. Like you tell it to the operating system to take back the memory from your program. Your program cannot use this memory anymore, and your memory is reclaimed by the operating system, which is what you want. No, that's the thing. It deletes the memory under the pointer. The pointer still points to that memory at this point. Again, we're going to talk about it a lot more. But this thing just frees the memory. It doesn't change the value of the pointer. So if the pointer was pointing to the address, I don't know, FF13 or something, I don't know, in this hexadecimal numbers, then after this operation it will still point to the same address. There will be nothing valid under that address. We can't use that address, but the pointer would still point there. And that is, I think, one of the biggest issues with a lot of beginners, that they think that after delete it's nothing there, but the pointer is still there, so they still try to use it, and sometimes they can, and again, it's undefined behavior, which is really bad. And that is why eventually people have thought for a very long time, many years, to make sure that we now have much better structures to deal with that, and much better ways of thinking about writing the code to never ever have those issues again. So again, we are going to talk about that. There are fixes for all of these problems. You won't have to think about that if you do things right. And again, prefer using smart pointers. You might have guessed smart pointers are smart and good. We are going to get to that. So a small example here is it's just what we were talking about. So for example, we create, like, we have some size 2, we have a pointer that points to nothing, and it's the same example as we saw for the stack, but now we use heap allocation. And it's a bit mangled over here because, again, place on the slide is finite. So what we do here is we create a pointer on the stack that points to nothing, and then we set it to address on a heap, and this address is just some array on a heap of size 2. Then we set those values for the array, and then we go out of scope. The idea is that we can still use this pointer. So before, in the stack example, we couldn't use this pointer to access values because it was freed, because that array was not in dynamic memory, and it was freed for us, right? Because we went out of scope. Now we have allocated it manually, and when we get out of scope, nothing is freed. We didn't create any new variables in this scope, apart from setting the address of the heap memory. So when we get out of the scope, we do not remove that memory, so we can still use it. And this is completely fine. So we can still print out all the values from the array because nobody has touched the heap memory. Now if we delete this heap memory over here, then we cannot access it. So we can, sometimes it will work, sometimes it will not, but we shouldn't because it's undefined. But it's only after we remove this memory. And again, whenever the program has ended, the operating system reclaims all the memory from our program on its own. Whatever we forgot to do and so on, is just if we want our program to run for a long time, we really should care about making sure that we don't kind of spill our memory all over the place. Okay, good. So now we've started talking about the memory leak a bit, and now I will try to explain it more visually, and maybe it will make more sense now. So memory leaks only happen when you work with heap memory. They cannot happen when you work with stack, because stack is managed for you. You cannot do a mistake there. So what is a memory leak? A memory leak is some memory that is allocated on a heap that we lost access to. Because the issue is that we cannot find anything that we don't hold an address to. We don't know, we don't have a magic function that will tell us what does our program use on a heap. We have to manage that ourselves. So if I create it, let's look at the example. Let's say this is our heap. It's a huge heap, and these are 2 pointers allocated on it. And we have a pointer 1 and a pointer 2, and they both point. This is the memory for the pointer 1, allocated for the pointer 1. This is the memory allocated for the pointer 2. And now what we do is we assign pointer 2 to the address of the variable of pointer 1, or just pointer 2 equals pointer 1. So now they both point to the same address. And now this is a big issue because this is leaked. We will never be able to restore that because we don't know where it is. there was some memory, now it's still there. The operating system still thinks that we might use this memory, but we lost access to it. We cannot delete it, because to delete it, we need to pass a pointer to it, and we don't have a pointer to it anymore. So the only way, like there is no way to remove that, and that is leaked memory. So that usually happens by mistake. In the programs where we had to manage all the memory manually, and that happened a lot, and it happens a lot if you try to manage memory on your own. There are tools to try to find those things and so on, but tools are very tedious to use and hard. I will not teach them in the course, but I will teach the method of avoiding this whole situation from the start. Right, so this is a small example of how to, like, how it all looks like and what can happen, what can be wrong. And it's just the same thing as we discussed on the previous slide, but in code. So we create two pointers. Oh, sorry, this should be null pointer. Null also works, but it's an old way of representing it. Null pointer is better. We won't go into details. We'll change it after the lecture. It should be null pointer, not null. So what we do is we create two pointers. They just point to two arrays in the heap memory, and then we set the pointer 2 to pointer 1. So now they point to the same memory. And if we print them out, they will point to the same memory. And then if we even do this, it will be a completely different error. But we cannot free the memory of whatever the pointer 2 has allocated here, because we're not pointing to that. And we see this beautiful error. Like, it's very small part of this error. So you can see this is the output of this guy. So 1, 2. And here it's like pointer 1, pointer 2. And now they point to the same memory. And when we try to use delete twice, we see this error. There will be a lot more in the terminal. It's a huge error. This is the top line of it. Whenever you see this scary error, double free corruption, it means that you've tried to delete something twice. It means that in this case, we have tried to delete memory under pointer 1, and then we try to delete the same memory because we have assigned pointer 2 to pointer 1. So we try to delete like free memory twice, and that is when we get this error over there. So whenever you see double free or corruption error, it means you have tried to free memory twice. Okay? And at this time, also the memory under the second pointer initially is never ever freed. I mean, our program has already crashed, so we don't care about that. But it was never freed, and if we use it, it will be leaked. Right. There are more examples for that. So, for example, if this thing you can run on your own, but beware, this code is dangerous to run if you have not enough RAM. What it does, it creates data, and then it creates arrays of size approximately 1 gigabyte each chunk. So every iteration, so it's just, we take the 1024 to the power of 3 and divide it by 8 byte, and we do it for a double array, and this will give us, so this, every of these is an array of size 1 gigabyte. So on every iteration of this loop, we will allocate 1 gigabyte of data. And we do 5 iterations of that, and if we stop at some point, we will, actually, I think I can show it to you, because I have those examples at hand. Listings. This one? Yeah, this one. So, if I Okay. Right. So for that, I will need to show my memory usage. And my memory is now at 4 gigabytes, 4.5 gigabytes out of my 11 gigabytes, or like 11.6 gigabytes available on this laptop. And let's see what happens if we run this. I will probably reduce this to 3 just to not completely destroy my laptop. And I need to run it from a terminal. So I will need another terminal over here. Let me make it big. Yeah, come on. Okay. It's memory leak 2. So let's try to build this. Minus std equals C++11. Out leak. Memory leak to CPP. Okay, so now we have built it, and we can run this leak thing, right? So if I run this, it tells me iteration 0, 1, 2 done, and if we go back to looking at my memory, now I am at 6 gigabytes. Maybe it's not very. Let's make it 4. So let me kill this guy. I need to compile it again. So, right. So now it's 4.5 gigabytes of memory allocated. I have compiled the code. Let me run it. And we'll see that my memory is growing. So now it's at 8 gigabytes. It was 4.5 right now. Now it's 8 gigabytes of memory being used, and it's because I have this line over here which just waits for my input until it until it ends the program. But why does it happen? So it allocates some data, it fills this data with something, some important work, shows us that the iteration is done, but the problem is that we only free this memory once, and the issue is that every time we allocate new memory, this guy will have a new pointer to it. Like so, this generates a new pointer to new data, sets it to here, and this way we lose all the other pointers that we had before on the previous iterations of the loop. Is that clear? And that's why when we clear the data, we only clear the last one. We only clear the last iteration, but not all of the iterations. And all the other memory is lost. So if we would have that in a function that would be just called from somewhere else, it would just be leaked forever until the program actually stops. And now if I just press whatever, if I give it some number, it stops the program, and my memory is back at 4.6 gigabytes. Okay? So I hope that kind of was relatively intuitive. The idea is that new gives you a new pointer to memory. Whenever you lose a pointer to some memory that you cannot delete, you've lost it forever. So we should avoid doing that. Right. Also, if you would have too many iterations and you wouldn't have enough memory for that, you cannot allocate too much memory, more than you have. At some point, the runtime will tell you, well, yeah, you're running out of memory and I can't allocate anything more, so here you go, I will throw you bad allocation error and I will stop the program from running. You can actually recover from this error theoretically, but I don't know any real software that does. So that's the idea. So if you're losing memory, if you're leaking memory a lot, then your program will stop with this error. On the Linux system, you have swap memory, which is when you're running out of your working memory, your system will try to use your hard drive as your RAM, and this is insanely slow. So it will copy things from your working memory into on your hard drive to use it as your working memory, and things will become slow. So when you run this example, make sure you either don't have swap enabled to see the error, or that you don't reach swap, because it will move things to swap and it will not move them back, and it will be a lot of pain of working with your system if you move things to swap. So just beware running this example. It's a single dangerous example in this lecture. Right, so there is a kind of the opposite, like the evil twin of the memory leak is the dangling pointer. It's a funny name, but it's kind of what happens when you point two pointers to the same memory. So let's say if I create a pointer and point it to some heap address, and another one too, and then I delete through one of them. So before I deleted the memory twice, now I actually delete the memory once, and I even do it correctly. I delete the memory, I set my pointer to a null pointer, so now I remove the memory and I set the pointer to null so that I don't point to that memory anymore. But the problem is that what I was not aware of is that somebody else points to the same memory. And that is an issue because now he points to the memory and he has no idea that it has been cleaned, so that it has been freed. So this pointer 2 guy who doesn't know what happened, he will still try to get something from that memory, and sometimes he will, but sometimes he won't, and it's a big issue. And that is like a huge issue in the real software, that if you allocate memory all over the place, then some parts of your program may not know that somebody has freed the memory, and this is annoying. So what happens is, like if you have those both pointing there, then you have the delete pointer 1, then you have the pointer 1 equals null or null pointer, and now this guy is still pointing here, so that's bad luck. And if you try to use it, again, it's even worse. It's undefined behavior. So the worst thing that can happen to you is that this actually works, because this will snowball into other errors in your code, and it will take ages to debug and find where you did this error. So try to use the techniques to avoid those errors in the first place, because they're really annoying to debug. Right. So there is also an example for that. Of course, again, it's good to try the bad examples on your own, because this way you see the errors that happen, and you can figure out that this is actually what is happening in the big program that you're running. This is just the same example as before. So what we do is we create a pointer to a pointer 1, we give it some data, then we create a pointer 2 and we point it to pointer 1, and we change some data and so on, and then at some point we delete pointer 1, and then we try to call the pointer 2, which doesn't exist anymore, but it will still have some value. Again, I will not go too deep into this now. Copy paste it, run it, see what happens. So why is this annoying? Of course, in these examples that I showed you before, it's easy to avoid the mistake. You just have to read through it carefully and then be done with it, right? The problem comes when you're using like libraries that don't conform to good practices, or when you're writing functions that don't conform to good practices, especially when your code base becomes a bit larger than 10 lines. So for example, this is a really bad example. You should never generate data in functions. You should never like allocate or deallocate data in functions with new and delete. So in this case, we have a function to generate data, and we have two functions that take a const pointer to const data, like const pointer to const integer. Yeah, so again, this is just like, you never really see those functions in real world anymore, unless you're coding in C or like old C++. We will never see them in this course, but it's just an example to show what can go wrong. And for example, I generate some data, so this generate data should generate me some data and give me some pointer to it. So now I hold this pointer in my data pointer, and then I have to pass it to functions. And if I cannot trust these functions, even though the whole pointer is completely const, nothing forbids these functions to free my memory. And that is really bad, because if I use this function, like it can be like if I use it for good, it's good, I can still use my data afterwards. But what if somebody wants to remove that data in the function? I have no idea that this happens, and I have no control over it. Whatever const I put there, I have no control over that. So they can still free my memory. And the problem is that at this point, should I remove my data? Should I not? Can I use it? Like so for example, in this particular case, we have those functions, and let's say the use data for good is a good function. It just takes the const pointer, processes the data that it wants to do. It's something very important. It doesn't matter, and it doesn't do any memory allocation or deallocation, which is what we expect the function to do. But then the other thing says, yeah, okay, I don't like you. I will remove your thing, and it just removes the whole memory. And the problem now is that if I don't look into that function, I have no idea what it does. So it's not enough for me to look at the interface or like the declaration of this function. I need to see the code of that function. And sometimes it's possible. I don't want to do it anyway, but it's possible. But sometimes it's not even possible when it's in part of the library, as you already know from some homeworks, right? So if I give you a library, you don't know what is written in the code. You just can use the function. So if I can use the function and I cannot trust it, I won't use it, and it becomes useless for me. And the issue is that now that I have to make a decision, after calling this function, should I clean my memory? Should I not clear my memory? What should I do? And there is nothing that I can do right here. If somebody has cleared the memory, I get a memory leak. And if nobody has freed the memory and I don't free the memory, then I have the memory leak. But if anybody has cleaned the memory and I clean the memory, then it's a dangling pointer, and it's also annoying. So there is no correct way out of this. Like if you do any memory allocation in functions or memory like freeing in functions, you're up for a very rough ride, and it's not a good idea. So never ever do that. And usually, yeah.
In slide 22, can you read me? If here we put a pointer to null pointer,
Where?
then what happens?
Can you tell me approximately the line, or like?
We have pointer 2, right? There are 2 pointers.
This guy?
Yes.
Okay.
And you said this is the problem after we delete
Yeah, because this guy yeah.
If we put it equal to null pointer, then what happens? Can we do it or not?
If I put it here?
If we also put pointer 2 equal null pointer.
Yeah, so if after this line I put pointer 2 equals null pointer, it's totally good, because then at least my program will crash if I try to. But I have to know about it, and that is an issue. The moment you have to know something that is not enforced by the code itself, it's a big issue, because you will forget. Like, it's just a matter of time. So at this point, I have to know that there are 2 pointers that point to the same memory, and if it's not documented, I cannot know it, but even if it is documented, I will not read it correctly, for sure. And that is why it's not a good idea. So it's always a good idea to enforce things, like make hard constraints in code that it's impossible to do it wrong, right? And we are going to talk about that later.
So the only thing that we need to do here is to put pointer 2 equal null pointer?
Yeah, in this case, yes, but...
and just one delete for pointer?
Yes. And that is kind of like, when do you delete, when do you not delete, so you have to think about it. And the problem is, yeah, exactly, it is complicated. It's not only complicated for you, it's complicated for everybody. And that's why a lot of really smart people have spent many years to make it less error prone, so to make sure that we cannot make errors there, at least unwillingly. Sometimes people still do it, I don't know how, but let's see. Right, so, and we come to a good thing. So this is the first relatively good thing. It's not the best thing yet, but it's a way to good thing. So before C++11, people started thinking, okay, we have this problem with the memory, and we understand that it's bad to allocate thing in function and to remove thing in function. What can we do about it? What can we enforce to make sure that our that it lives exactly the time that we need it and it gets removed automatically? And for that, people have, like, C++ community is outstanding in their abbreviations. So this abbreviation sounds like RAI, and its resource allocation is initialization. It's a very important concept. Whenever you create something, it should own its resources. Whenever it gets removed, it should free its resources. It's very, very, very simple. And the way to enforce it is to use classes. If you use your own custom type that encapsulates everything about this type, you can guarantee that whatever resources you were using, they will be freed in the end. And it doesn't matter what it is. It can be a pointer to a file. It can be like some strings or some other data and so on. And you can do it like this way. So the very simple implementation, it's not enough to guarantee complete safety, but it's good enough for the start, is if I have some data over here and it's my private member, and in the constructor I set it to something, so I create some new memory for it, right, in the constructor. So the moment I create an object of this file, this object allocates memory. The moment this object gets removed, say it goes out of scope or whatever happens to it, it deallocates this data, and then I'm completely safe, right? Well, not entirely, because I still can't copy this, and we are going to talk about this now. But at least we can now allocate and deallocate things. So what we basically do is we want to make sure that our data is kind of scoped here. And before C++11, it didn't really make much sense, because you basically then create a variable that will live in the scope in the end, because you will create an object to this variable in some scope. So by the end of some scope, this object will get removed. It will remove its data, and it doesn't really make much sense, really. But in C++11, when the move semantics were introduced, and that's why we were talking about moving things, this started making sense, because now you can move your data when you don't want to deallocate and reallocate it. We are going to see that in examples more later. So why can't we copy this data? So let's see. So if this is a class, this is like a quiz. Like it might take some time, but I want you to try to tell me what is wrong here. So there's definitely something wrong, but I want you to try to tell me what. So what can be an issue here? So again, what you have to think about is, first of all, what constructors are generated automatically. So say, what will be the copy constructor of this class? How will it look approximately? And then, how do you copy the pointers? What does the pointer assignment look like? We just did it before in the slide. So how does it look like, and what can be an issue that starts from there? Okay, any ideas? Let's just discuss it. Yeah?
The copying of the pointers is done by setting them equal.
Yeah. Yeah.
And then we have actually, because we have one pointer who's pointing to delete it.
Yeah, that is exactly right. So I mean, it's not entirely right, but it's definitely in a very, very, very right direction. So you're nearly right. The problem here is that our class generates a copy constructor for us, and this copy constructor, it doesn't know about our memory stuff. It doesn't know that it needs to deallocate and reallocate memory. It will just copy the pointer over. So what we will have after creating a copy of the object A is we will have two objects with data pointing to exactly the same memory allocated by the object A. And when by the end of the scope these both objects will be removed, they will both call their destructors over here on the same memory. And this will cause our double free or corruption error, because we now have two pointers that point to the same memory, and they will both need to be removed because they are part of the objects in the scope, on the stack. So they will be removed sequentially, trying to free the same data and so on. So that's why if we do the proper RAI thing, then we need to allocate and deallocate memory on our own in everything. And then we need to go back to the lecture where we were talking about this move semantics and so on, and the rule of all or nothing. And we will need to implement, whenever we implement a destructor, we will need to implement the copy constructor, the assignment operator, the move constructor, and the move assignment operator. And nobody wants to do that because it's annoying.
So both line 13 and 14 are the problems? Or?
No, so in this line, this will happen, right? So some data is allocated once for object A. This line, there is no function here that will be called. This function is generated automatically for the class. If you don't write your own copy constructor, one will be generated for you. And it's going to be a very simple copy constructor. It's just going to copy all the variables to another class. So what will happen, it will look, okay, this variable is of type pointer to something. Okay, I will just copy it over. So now you have a copy of that pointer, but you don't have the copy of the data. Your data is allocated only once. Now you have two pointers that point to the same data, but now you reach the end of the scope, and now these A and B get destructed. They get destructed by calling their destructor. And they both try to remove the data that they think that they own, but only one of them actually owns this data because only one of them allocated this data. The other just has a pointer to that data. So when it removes it, we get this error over here because it tries to clean the memory that A has already cleared. Okay? Good. So the concept of this problem is called shallow and deep copy. Like whenever you copy pointers, there are two ways of copying them. One is shallow, the other is deep. And these names are relatively self-descriptive. So a shallow copy just copies the pointer, doesn't copy the data. Right? Sometimes you want to copy the pointer and you don't want to copy the data that lies underneath. And the deep copy is you actually want to copy the data over and make sure that you've deallocated the old data, reallocated new data, and so on. The default copy constructor only can implement shallow copy because it doesn't know about anything apart from it. So when you're using this RAI and shallow copy, you get a dangling pointer. But if you use RAI and rule of all or nothing, which means you actually implement on your own all of the other five special functions: the copy constructor, the copy assignment operator, the move constructor, the move assignment operator, and the destructor, then you're safe. Because then you've implemented the correct copying of allocating more data, copying the pointer to that data, and so on. But the good thing is we don't need to do it. We don't need to do it now anymore. There are smart pointers to the rescue. And smart pointers are basically, it's a class, just as the classes that we have written before. So your image class is just the same way implemented as the smart pointer. It's just a class. And these class, they have a raw pointer inside of them. They own this raw pointer, and they manage its lifetime completely. So they manage its copying, they manage its moving, they manage its deletion and creation, and so on. And you should think about smart pointers as something that owns, like it's all about ownership. Like they were created exclusively to manage heap memory. You should never use them with memory that is on the stack, and they make using heap memory easier than otherwise. Whenever you still have some function that just takes a raw pointer, and it should just work because you maybe want some polymorphic type or something like that, but it shouldn't own that pointer. Just use raw pointers as normal, so the ones that we have discussed before. But whenever you need to allocate memory or copy memory or deallocate memory, whenever you need any single one of these operations, then you must use the smart pointers. And there are basically now 3 smart pointers: the unique pointer, the shared pointer, and the weak pointer. But we are going to be talking about 2 of them in this course. We're going to be talking about the unique pointer and the shared pointer. Right, so I think actually this is a good point to stop today. So we are not going to go, because now we're going to be diving into the unique pointer and the shared pointer, and I think it's a good way to just repeat these 2 slides on the next lecture and start with smart pointers. So it will be helpful for you for tomorrow to be relatively comfortable with everything that we discussed today, with just thinking about pointers at all, because smart pointers behave like pointers with additional things. So we're going to talk about that. But I guess for today, that's all what I wanted to tell. So see you tomorrow. Thank you.